In this section, we'll take a look at implementing convolutional neural networks. First, let's take a look at a potential solution to the assignment from the last section. So here's my solution. I'm actually reusing our encoder with the same mixed CSV dataset we actually used for the regression video last. And I actually pull out the categorical column that I think is research, and serial number is a discard column. And I'm using this admissions prediction dataset from Kaggle to predict the chance of being admitted to graduate school. I actually changed a couple of things in here. I'm using a different batch size, and then in particular, one thing I wanted to do is have 256 epochs. Like, I really wanted to run this model for a good long time and see how it went. And then as a reminder, at the end, I used the R-squared score with a single batch of all the things in the test data. Now in this section, we're going to take a look at convolutional networks for image analysis, convolutional concepts such as filters, strides, padding, pooling, and sizes. We'll go ahead and implement a convolutional network. We'll visualize the effect of the individual convolutional network layers, and we're going to implement an end-to-end convolutional network across images to do image classification and recognition. In this video, we'll start off by learning about convolutional networks for image analysis. Learn a few concepts here. What makes a convolutional network? Why use a convolutional network? And why are convolutional networks effective on images? All the networks we've used have been dense, fully connected. A convolutional network is actually partially connected into regions or patches, and convolutional networks as a result of this can be more computationally efficient because they don't have to actually compare every input by every parameter when they do the math. These little regions or patches are thought to be similar to what a human visual system does by finding areas of an image that are most interesting or salient. So here's a diagram to give you a sense of the different topologies. A dense network here, you can actually see every one of the inputs on the far left is connected via parameters to every one of the outputs on the far right. So there's actually a huge number of computations going on. The convolutional network, on the other hand, on the right, each one of the input parameters, you can see the lines, is connected to simply 3 of the parameters in the middle hidden layer, and that's really where the convolution is. We actually stride across the model, showing a connection for each one of the 3. Now the actual value 3 is totally arbitrary. This is actually one of the parameters you can pick, so we'll actually dig into that into the next video. So with the striding, what is an image actually doing here? Well, a convolution, step by step, it divides an image effectively into regions, that it applies a convolution to each one of those little regions, and then it uses this convoluted or convolutional output to feed into the next layer. This is different than having every input pixel be transformed by the parameter matrix. Instead, it's focused on individual subregions of the overall image. Then when you go in to turn this into a network, the topology changes a little bit. You actually have an input image, which is actually the raw data encoded as a tensor. You have a series of convolutional layers that make these transformations to extract interesting features. And then finally, you do turn back to a classic dense network in order to do your final output classification. So typically you'll see neural networks working on images implemented in this fashion. Input, series of convolutions, final dense transformation into a series of classes in order to classify the image.